He'll be speaking on the emergence of irreversibility in quantum systems.
Thank you. First of all, I would like to thank Thomas and all the organizers for all the effort in leading to success this Congress and always coming with the great interest and pleasure. Thank you for this continuous effort. And today I would like just to report some work we've made on the emergence of irreversibility in quantum systems. This derives from a collaboration with Vlatko Vedra and Chiara Marletti in Oxford, and in particular in my group we collaborated with this work Alessandra, Ettore Bernardi, Ivo De Giovanni, Marco Gramegna, Fabrizio Piacentini, and Laura Minoldi, now is back in Argentina. So, which is the point? Of course, the point of the emergence of irreversibility from time-symmetric physical laws is a central problem in contemporary physics since a long time. There are several approaches for getting this irreversibility. We have statistical mechanics methods, information theoretical description of logically irreversible tasks, classical and quantum thermodynamics from laws, and so on. Anyway, in all these cases, there is always a tension arising between the laws describing the irreversible phenomena and the time reversal symmetry of macroscopic dynamics. Here in this talk, I would like just to express our attempt to express irreversibility in the frame of constructor theory, as the requirement that this transformation is possible, while its inverse is not. So let's describe a little bit more in detail this idea that you can find all the details in this paper. Okay, of course, the point is very similar to Jones' experiment. You have, in this case, a volume of water. This can be heated up by mechanical means only, but of course it's impossible to cool it down by the same means. So we have, in this classical example, typical example of a process which can be realized in one sense and not in the other. Now let's try to formalize a little bit better this in constructor theory. So constructor theory was introduced by Deutsch and Marletto. You can find details in this paper. So the idea is just to introduce few definitions. The first definition is a task. What is a task? A task is just a specific physical transformation, particularly in qubits, and you are going from some density meters to another density meter. So it's physical transformation. The transpose task is just the reverse. So you're going, in this case, from rho x to rho y, here from rho y to rho x. Okay, so then I still going by introducing a few definitions, but very few don't care. So we define a substrate qubit on which this task is defined as q, and the rest of qubit as r. So a constructor for the task on some substrate is some subsystem of the rest of the world that enable the task. So without undergoing any change in its ability to do it again. So it's some sort of machine in the rest of the world that allows you to perform this task and undefine the number of times. So you can repeat the operation. So a task is possible if there is no physical constraint on accuracy to which the constructor can perform it. So it can have an arbitrary good accuracy in performing this operation, and impossible otherwise. A constructor-based irreversibility is defined by the fact that there are situations where the task T is possible, but is transposed, and is reverse is not. And in the rest of my talk, I try to explain you why this could happen. So let's put this consideration in a little bit more precise mathematical form. So we have a fixed task on a certain substrate. We define an accuracy epsilon, larger than 0, of course, and we define a set of quantum states of the rest of the world as the system that can perform this task with an accuracy 1 minus epsilon. So mathematically we have just these systems in the rest of the world that allow a unitary operation acting on my system and the rest of the world and producing a certain results, where these results is in a very small ball with an accuracy 1 minus epsilon for the fidelity around the target that I want to reach. So this is just for formalize this definition. No? So the other point is that I would like to repeat this operation several times, so I repeat 1, 2, and time, and I wanted that this system of realizing the task can operate indefinitely without deteriorating. So we must introduce now a measurement of how the system can perform the task after n repeated usages to an accuracy 1 minus epsilon. So we introduce this relative deterioration after n usages, which is the ratio between the value of epsilon and this S, which is the smaller fidelity that can be realized after n repeated usages and the initial system. Okay, so the two conditions at this point for a constructor realizing the task with a certain unitary law is that we have an empty, non-empty set of systems that can perform this task, namely the task is realizable and the task is realized in a way such that the system can be used an indefinite amount of time, so that this relative deterioration is going to zero. It's not, the system is not deteriorating. So, what is the point behind all this discussion that you can find described well in this paper of Chiara and Maria Violaris? So the idea is that, of course, you have some unitary operation you apply to your initial system and to the rest of the world, and you obtain a certain output. So what we are saying is that that there are tasks that can be realized in one sense and not in the other. Of course, if you have a unitary operation and you consider the whole system, and of course this unitary operation acting on your system and the whole universe is entangling also the different degrees of freedom of the rest of the world, you can always find an operation inverting, a unitary operation inverting with this. But the point is that what you cannot find is the situation which we are going to describe, where you consider just the system evolving in one sense, then of course you cannot reinvert all the universe. So you take your system, you take an inverse operation, and you try to come back, but without acting on the whole universe, but acting on your system, a part of it. And while in one sense this task is realizable, in the other is not. And this can be visualized with a very simple example. So let's consider the quantum homogenizer that was introduced in this paper. The quantum homogenizer is just a partial swap that happens with just a certain probability given by this coefficient, otherwise it is an identity operator. No? So you act with this homogenizer, so you have your qubit, and this qubit is interacting with the rest of the world and is partial swap. Okay, so we look to what happens with the partial swap with this homogenizer. So consider now two specific cases where ρx and ρy are either a pure and a maximally mixed state. So when we try to go, we start with a pure state and we go toward the mixed state, we can realize a constructor for the task. One can see that you take the homogenizer, you apply, and indeed this definition of deterioration is going to zero. You can realize faithfully the task and so on. So the task has a constructor. But when you start from a mixed state and you try to go back, just by using the inverse operation, what you can see is that this definition of the deterioration is going to infinity. So that the inverse task has not a constructor. Okay, this is a simple example, but of course when you have a more complex system with more degrees of freedom, you expect that this is even more evident, where one task can be realized in one sense, so you have a constructor, but when you try to make the inverse task, you don't have a constructor. So it's possible to go from pure to mixed state. So this is somehow is a typical situation in quantum mechanics, where you have the coherence, you are going from a pure to a mixed state, but it's not possible to have a constructor for coming back from the mixed to the pure one. Okay, so this is just the theoretical description of this idea. Then we try to demonstrate it at work in the experiment. So the point is just to use a single photon source that is described here. I will not bore you with details about the experiment, but the idea is just to have a laser that produces two pairs of photons in a nonlinear crystal. One is just triggering the presence of the other, and this is the typical rounded photon source. We build this very low noise rounded photon source, so you have a very good realization of a single photon. Then you prepare in a polarization state, and then you address this photon prepared in a polarization state to a series of quantum swap that can be realized with a certain probability and provide the realization of this homogenizer. So you can consider the two situations. You start from a pure state, which in a qubit basis is 0. It means, for example, that you have selected the horizontal polarization, and you go toward a maximally mixed state. So what happens is that you add a certain number of these homogenizers, and the state is moving. This is just the value of rho 0, 0, and rho 1, 1 toward a mixed state. Then you try to make the reverse. Of course, you can do also in this sense, but what you observe is that you have different behaviors, both for the accuracy, but in particular for this parameter describing the deterioration of your operation. So when you go to pure to mixed, here is just what you expect theoretically compared with what we obtain with the experiment. You can have good fidelities in both the cases, but when you consider this deterioration, relative deterioration that I have defined before, you have that while in the pure to mix, this relative deterioration tends to 0, so you have a situation where you can repeat this operation all the time you want. When you go in the other sense, from mixed to pure, the relative deterioration is growing, and indeed this is what makes impossible the realization of a constructor for the transposed task. So the operation pure to mix as a constructor, the operation mixed to pure does not have a constructor, and our experiment showed that this is indeed the case. This does not depend really on the parameter choice of this partial swap of this homogenizer. Indeed, present here for one value of this parameter. You remember the homogenizer. No, much. In our definition, what is the definition of the homogenizer? Okay, it depends on this parameter. Substantially, cos theta identity plus I sin eta. Okay, here. the subquantum partial quantum swap. So here you see these conclusions do not depend strictly on the homogenizer, rather generic results. So you can change this parameter eta and the situation is substantially the same. So you have a deterioration in the case of pure to mixed, you don't have deterioration in the case of mixed to pure. So our experimental results confirm what we have described in the theory, namely that you can find a situation where you have an homogenizer implementing a task, and in this situation the homogenizer implementing the task always outperforms its counterpart that realizes the reverse task. The reverse machine suffers of a much higher degradation than the one realizing the task, and actually at the end it fails to be a constructor. So you have a constructor for the task T, but you don't have the constructor for the reverse operation. So this is a typical situation of irreversibility. I can go in one sense, but if I try to reverse the operation, I fail. So we think that this provides at least a framework for describing how irreversibility can emerge in quantum mechanics and in the frame of constructor theory. So we think this is an interesting result that eventually can be further developed. And we've also shown in an experiment how this theoretical framework can actually work. And I think that visualization of how the theoretical ideas really can happen in the world is always very useful and significant for understanding them better. Thank you for your attention.
Time for questions.
It's very nice to have this explicit microscopic constructor. Of course, nature is full of them in practice, as we all know. And my remark is only a little one. We usually speak about the direction going from pure states to mixed states as the ones, you know, where we have irreversibility. But you can, of course, also have the opposite. Once you look at subsystems, you can also have mixed states going to pure states. And I give you very simple examples. Almost all our atoms are in the pure state, even if they have been in the mixed state in the past because they have been at higher temperatures or something like that. So there is not really a single direction that it always goes from pure to mixed, which is interesting for certain entropy considerations. You can also have constructors that go from mixed to pure, and I think it would be nice to realize, to think a little bit how to realize for them also a simple experiment, just for demonstration of something that we know happens in nature, but you see it then microscopically.
Yes, this is an interesting suggestion. I think we can consider it. Indeed, our example is not for showing that you always go from pure to mixed and not the reverse, but for showing a specific example where you don't have a transpose task. This would be interesting. It can be a further step in our work. Thank you.
Yeah. In my mind, the process of homogenization is just an abstract, simple model of equilibration. So you have your initial qubit, rho x or rho y, rho x, which is either pure or mixed. Now, the homogenizer is a reservoir of, say, infinite or a large number of qubits, which are the target. Identical qubits, capital N in number, and they are the opposite. If you go from pure to the mixed, then the reservoir contains the mixed states, repeated by a large number. And if you go from mixed to the pure, then the reservoir consists of a large number of pure states. Now, I don't see why the reservoir is a large container of many identical qubits. I don't see why it would become more deteriorated in one way than the other.
Okay, the point is just, of course, what you are doing is that, as in physical world, you cannot consider the whole universe. No, so you have your system, and this is interacting with a part of the reservoir going in one deterioration, and you apply this task. Then you go, for example, from pure to mix, and you see that what happens for further and further application of this, about the accuracy and about this definition, which is a specific definition of the deterioration. I would like to come back to this. So it's just the fidelity of the qubits that you have. Then you make the reverse task. Okay, this is the fact that this fidelity, so the specific definition of the deterioration, is changing in a different way in the two cases is exactly what you observe, but also what, if you make the calculation, I can give you the explicit, actually you find the explicit calculation. I am not reporting this talk because a little bit boring, but you can find explicitly here. And I think there is no mistake, but also the experiment was taking this. And you really observe this kind of material. But okay, these are just in the supplementary material of this paper. You can find the details.
Please, maybe I missed something. You have a homogenizer which swaps your qubits with the reservoir, and as Lau said, this is some sort of an equilibration process. So I do not actually see what the difference between your constructor approach and the usual quantum dynamical semi-group approaches and decoherence. We see irreversibility even in that sense.
Of course, there are always analogies, and I think in our idea, this constructor framework is very clear, and because you have this clear definition of what is a task, what is a transposed task, when the task is realizable, namely as a constructor, when it does not. So there are certain definitions that, in our opinion, make this very clear. I'm not sure that in the evolution of this dynamical semi-group is as well, everything is as well defined as here. But of course, this, as in many discussion about the interpretation not only of irreversibility, but in general foundation of quantum mechanics, different people have different opinions. But in our opinion, this is by far clearer.
But these are talking about the same things, right?
Sorry?
These are describing the same phenomenon, right?
I am not completely sure. Of course, irreversibility is the same phenomenon. If the way in which they are describing is exactly equivalent, I'm not sure.
Because like your task, you do not want to transpose, but then in the semi-group approach, it is the same idea, right? You can time only increases in one direction, which cannot go in the other. Phase becomes smaller and smaller.
Yes, but you don't have this definition of deterioration, of accuracy of the task, etc. that you have here.
Okay, thank you.
Yeah, I have a somewhat similar question. I was wondering how this, what you presented, was of course profits from the clarity of the definitions, but how this relates to the previous talk. Because there we have seen how this non-emission Hamiltonian comes out, and in the presence of acceleration, or let's say in the presence of gravity, is that what ultimately makes the universe irreversible? If you
Maybe
decom-
also the idea of how can be reformulating the constructor theory. They don't point exactly to the same.
I think so. Both are the effect of a non-unitary evolution. You can take a few techniques using this evolution. Yeah.
This is a framework for formulating a certain idea. No? Probably you can reformulate that idea as well in this constructor framework.
If I'm allowed to give a second comment or question. Actually, I find it very nice that you have this possibility of realizing effective irreversibility with only relatively few qubits as well. We do not have to go always to the limit of very many. Because what you could study in principle is really where the information goes. Since the overall thing, you know, it's unitary. And so somewhere the information has to go somewhere. And I think it's actually going in high correlation functions between the reservoir bits that you could in principle even try to measure. And that also gives an answer to your question why the system changes in one direction differently from the other ones. Because actually what you have, you shuffle the information into high endpoint functions of the reservoir, and then if you want to go back, you would have to track that out again, which is literally impossible, because actually in practice you would prepare it so accurately the way back that you really can extract from these high correlation functions the information again. So I think that's a very general way how to understand equilibration and irreversibility, that things go to unobservable high correlations, and in your system you could even make that practical by just measuring or at least calculating what happens to the information, how that is distributed among into correlation functions of your reservoir bits.
Yes, indeed it what I was mentioning in this slide, that you can find some discussion in this paper of Maria and Chiara to provide more details on the line you are saying, exactly this.
Sorry, how many qubits are there in your system and environment, like reservoir?
Oh no, we have one qubit interacting with 4 or 5.
Oh.
So it's a small reservoir. Indeed, you can see here the numbers. This is the number of interacting qubits. But then we describe theoretically growing number, but of course in experiments you are always limited. But already at small numbers you already start to see this effect.
Okay, so I think there are no more questions. So we'll end the first session. Okay. Yeah.
Are you sure that there is no other source of decoherence?
Actually,
Or like, you know, as much as is possible?
let's say if we don't have an interaction and the photon arrives again without having lost the fidelity is 99 point something percent. So. Okay.
Okay, so let's thank all the speakers for the